Looking at lesson 3, which is on calorimetry here, if you were in class the other day and we did the specific heat lab, we actually used a simple form of a calorimeter, but I did not call it that just because we hadn't talked about that word yet. But if you think back to that lab, that will help make sense. So in that lab, you used an insulated device that you used to measure heat release or absorption. If you think back to when you put the different metals in a styrofoam cup and you had a thermometer in the cup and you're measuring different things, that is a simple version of a calorimeter kind of shown here. Okay. Now, the more cups you do nest together, the better your results are going to be. We will be doing a lab tomorrow that looks a lot like this, where we're going to have a metal can kind of suspended over a cork with a food sample that you're going to be lighting. You're going to try to see how much heat the water absorbs that's in the can because of this flame, because of the food burning underneath. And here's a really intense looking calorimeter. There's many different kinds as you see here. This one is actually a bomb calorimeter where you can set up ignition wires and literally put a bomb sample in here and have it explode and then measure the energy that's released. Okay, so this are just a couple of notes about these. Use the conservation of energy, which is heat gained is equal to the heat lost to measure different calories. Physical calorimetry involves mixing two systems to reach some final temperature. Chemical calorimetry involves the reaction of one system. And then the key to doing these problems is to identify which system is gaining heat and which is losing heat. So looking at these types of problems here, we're going to do some examples. So the main equation used is the Q of the systems, or the heat of the system, is equal to the negative Q of the surroundings, which would be the heat of the surroundings. That's showing you that negative sign is saying the heat released by one side is the heat gained by the other. That's how you just adjust for it. So looking at this first example, we have a styrofoam cup initially containing 10 grams of water. Your C value there for water. You have a temperature. You add 186 gram iron ball to the water. Final temperature of the water and the iron ball is given to you. What's the specific heat of iron? This feels a lot like the problem we did, or the lab we did the other day. This would be if you're given to in a certain situation. You actually did these types of calculations. We just didn't set them up exactly like this, but we were still using the Q calculation. So looking at this, we've got our Q of our system is equal to negative Q of surroundings. I'm just going to call the system the iron, okay, and the surrounding I will call the water, okay. So we've got, if you think about Q on either side, is the same equation we've been using, so MC delta T equals negative MC delta T. Just make sure on one side you only put the values for the iron, and one side you only put the values of water. So I'm just going to do iron over here and water over here, so keep things straight. So our M of the iron would be right here in the problem. So I'm going to plug in 186. Our C of the iron is what we're solving for. But I know my delta T of the iron. Okay, so the final temperature is 80. The initial was 90. So that means 80 minus 90 is negative 10. Okay. All right, now, looking on the other side, I have my negative sign just from the equation up here. The mass of the water we were given is 10. Okay, so 10 grams is plugged in here. This is our C value. I'm going to plug that in, 4.186. Our delta T, we know that the initial temperature of the water was 60. The final was 80. So 80 minus 60 is 20. I'm going to go here. So I'm plugging in all these values to solve for this number right here, this C. Okay. All right, so 186 times C times 10 equals negative 10 times, this should be a 4, sorry, 4.186 times 20. So you go ahead and you solve for that C value. Your specific heat of iron should be 0.45. And then your units are always joules per gram degree Celsius. And that's it. Okay. Now they can look a little different like the next problem. So we have hot water at 90 degrees Celsius is poured in 100 grams of cold water at 10 degrees Celsius. The final temperature of the mixture is 70 degrees Celsius from the mass of hot water. Okay, so this problem, notice that we only have water on either side. Okay, so I'm just going to write out the same equation. Q system equals negative Q surrounding. Pick one side that you know what's going where. So I'm just going to put on the left side here, I'll just put my hot water. Everything on the right is cold water. So hot water on the left, cold water on the right, just so I keep things straight. So I've got MC delta T equals negative MC delta T on this side. So I need my mass of my hot water, which I don't have. That's actually what I'm solving for. So I'm going to leave M here. My C for water is 4.18. Okay. Delta T for water, hot water. I know that my initial was 90. My final was 70. Find delta T, always do final minus initial. So 70 minus 90 is negative 20. On the other side, I've got negative this is all cold water. So cold water, I have 100 grams. It's still water, so C is 4.186. And then I know that it was initially 10, it was finally 70. So final minus initial is 70 minus 10, which is 60. Okay, so I'm solving for my M value here. Looking at this, I take 4.186 times negative 20, and then set that equal to negative 100 times 4.186 times 60. When you solve for this M here, just rearranging, doing some simple algebra, you should get your mass of the water is 300 grams. Now, if you were looking at this to make your life a little easier, the 4.186 is on either side, so you can cancel those if that makes solving a little easier. But if you just plug it into your calculator, either way, including the 4.186 on either side or getting rid of it, you should start 300 grams. All right, so you're going to try out some more problems like this in your homework and then in lab tomorrow to see if you understand how to do these calculations.